Let's do some center of mass calculations. We'll do a quick review. Let's say I have a meter stick, 2 kilograms, 1.5 kilograms, and 3 kilogram masses hanging from this at 30, 80, and 100 centimeters. And we want to find the center of mass. In other words, where would you put a pivot to make this thing balance? I'll take a guess. We'll assume the meter stick is massless, and we measure the distances from this pivot to these weights. If this is going to be X from the pivot over to here, this distance is 50 centimeters, so that means this side has to be 50 minus X. Then we have to figure out the distance from the pivot out to this weight. I suppose you can say that from here to here is 50 minus X, and then we're going to add another 20 centimeters. We want the torques to cancel about that pivot, because then the center of mass would be right over the pivot, and it won't fall to either side. The weight of this mass times this distance would be the torque counterclockwise. The weight of this mass times the distance would be the torque clockwise, plus the torque created by the last weight. You can see the G's cancel out, and after some algebra, we can say that X equals 27.5 centimeters, or 57.5 centimeters from the left end. We'll remember that right here. But this is clumsy. Imagine if you had more masses. There's got to be a better way. The easiest thing to do is to set the math up with the pivot on this end. That means that you're going to have to know that the finger is going to have to push up with whatever it takes to hold up all this weight. And since we saw that the G's cancel out, we'll just leave them out. Now this idea works because if the torques cancel out about a pivot, they have to cancel about any place that we want to call the pivot. Imagine just because I call some other location the pivot, that's not going to make the whole thing collapse. It's already balanced. We'll call the distance to where my finger would be to hold this up, the distance to the center of mass. Now we'll get the torques to cancel out about this pivot. What does this mass want to make the stick do? It's going to want to rotate it clockwise. They're all going to make it want to rotate clockwise. So what's going to make it go counterclockwise? Well, that would be my finger pushing up. And you can see how easy that is. It's just however hard I have to push to hold the whole thing up times the distance from the left end. It's a lot more straightforward. And that's because instead of having all those parentheses with the minus signs, we're replacing that information with the total mass of the system that we would have to hold up. It's the same amount of information. It's just a lot neater. So let's generalize all this. You'd have an M1 times an X1, M2 times X2, M3 times X3, and it could go on. On this side, mass the whole system times the distance to the center of mass. Now, technically, these are not torques. They're called moments. It's a mass times a distance. If you wanted to throw in acceleration due to gravity and make it a force, then it would become a torque. I think you can see it could be written like this: the sum of each mass times a distance divided by the sum of all the masses. That's how we can get the distance to the X center of mass. And that works great for what we call discrete masses. These are separate masses at positions. Well, what if I had a rod with a total mass m and it was length L? How could I modify that formula? You have to imagine that we have a mass of dm, a small increment of mass, and there'll be an infinite number of them. This is a continuous mass distribution. X equals 0 on this end. X will increase for each dm going down the line. The formula in this case won't have individual discrete masses. It will have many dm's, each one that far from the left end. dm times x would be a moment. How do I get them all together? I want to add them all up. Instead of summing discrete values, we integrate. That's called bringing them together. We're adding them up, but there's going to be an infinite number of them. And we'll divide by the mass of the system. Now in calculus, you normally would reverse this. and write x times dm. But our increment does not match the variable we're integrating. We need to consider using something called linear mass density. It's the mass per length. And that's the Greek letter lambda. Sometimes we'll have to use the area mass density, which is mass per area, and that's a Greek letter sigma. And sometimes we'll use the density that you're used to, mass per volume, that's volumetric density, that's a Greek letter rho. Since this is treated as a rod of one dimension, it's linear mass density, we're going to assume that the density is uniform, so that if we cut it up into little pieces, each dm divided by dx would be a constant value. Rearranging, we can say dm is equal to lambda times dx, and now we can get rid of dm. I'm putting parentheses around the lambda times the dx to make sure you realize that's dm. The lambda can be moved out because it's a constant. Now we can take the integral. We have 1/2 x squared. We'll put in our limits from 0 out to L, which will make this L squared. Now we can replace lambda, m over L. The masses cancel. L cancels with the L squared. And we just found out that this x center of mass is right in the middle of a uniform stick. Isn't that nice? Good use of calculus. Well, why would I do something so silly as to waste all this time using calculus to do something we all know? Because this technique will be applied to problems that we don't know. For example, what if we had a rod that did not have uniform density? The density increased as we moved down the line. You start with the same calculus integral, just like we had before. But this time, you can't bring that lambda out here because it's not constant. Depends on x. Now, can you see that that's lambda times dx? Well, we can bring the c out because that's a constant. Combine these x's, and that's something we can take the integral of. Raise the variable by a power of 1, we're up to 5/2, multiply by the reciprocal of the new exponent, and now, putting in the limits, a trivial case now. But how do we simplify this? What do I do with that mass down here? Hey, I don't even know what the mass is. The mass is going to be the integral of all the little masses. We can see that the dx is just the width of this mass, and that's going to depend on the linear mass density as we go across the rod. Remember that the linear mass density is dm over dx. So we can write lambda dx is the dm, which is cx to the 1/2 dx. We raise x by 1 power, multiply by the reciprocal of the new exponent, throw in the limits. Well, that's the mass. Put it right over here. And we can see that the constant cancels. And we're going to get some canceling over here. When you divide, you subtract the exponents. So we get L 2 over 2. It's just L. The 2's cancel, and then we can bring the 3 up. And we get an x center of mass of 3/5 L. Now, isn't that interesting? The mass doesn't affect the answer. It's not in here. It's the distribution of the mass that matters. Also notice that we can just check to see that this is just has units of meters, which that has to have. So at least in that regard, we've got something that makes us feel like we've done something right. If this was an L squared or an L to any power, you know you did something wrong with your calculus. Now just think if this makes any sense. Is this less than halfway or more than halfway across L? It's more than halfway. How come? If you know something about an x to the 1/2 power, the graph of lambda versus x is going to look something like this. Well, that means the density is increasing on this side. Yeah, that's the heavy end. It should have been over there. You can get an estimate for where you ought to be and see if it agrees with your calculus. Let's try finding the x center of mass for an isosceles solid triangle, length L. Well, you know that the y center of mass is going to be right along this dotted line, just due to symmetry. So we'll just find the x center of mass for the upper half of this triangle. I'll call this part H. How do I use this formula now? I have to have a dm and figure out how far it is from the left end. I can break the shape up into a bunch of rectangles, but the height of the rectangle is going to increase. I'll call this height y. That's dx. This is where x equals 0, and we'll say dm is at a position x from that point. Do you think I can use linear mass density to get rid of the dm? Well, this has an area to it now. I'll assume that the density is uniform throughout this object and say that the area mass density, which is mass per area, will also be equal to a dm over a dA when I cut it up into little pieces. So I can say that the dm is equal to sigma times dA to get rid of this dm. Well, there's only one problem here, and that I'm integrating x, but I have my increment is dA. So what is dA? It's the area of that little rectangle. Well, I think you can see that y times dx would have to be dA. Well, we solve that problem. We have a dx, so we can integrate x. But now I've introduced y. Y is going to be changing. Maybe you can see a similar triangle here. X, y, L, h. We can say y is to x as h is to L. So x times h over L is y. Now this can all be simplified. We can bring the sigma outside, and now we'll combine the x's, bring the h and the L out, and take the integral. 1/3 x cubed, throw in our limits, cancel L, and now what about that sigma? Well, that's mass per area. Hey, we can get rid of the mass. Well, we're certainly getting down there. But what's the area? Hey, it's the area of a triangle. Well, that's 1/2 base times height. The h's go, the L goes, and the x center of mass is 2/3 L. A couple of interesting things here. Notice the area density did not matter, nor did the value of h. It doesn't depend on h. It doesn't matter how steep the triangle is. It's just a triangle. Well, let's just see if that makes sense. That's the light end. That's the heavy end. Yeah, sure. We're past the halfway point. Still don't believe me? Cut one of these triangles out from a piece of cardboard. Measure out 2/3 L. Put your pencil there and spin it. It'll spin very nicely if it's balanced. Or you could just hang it from right above that center of mass, and it'll be balanced in this position. Imagine we take a wire and we make a semicircle out of it. That's the center. Where is the center of mass for this wire? Well, in the x direction, I think we can see that it's going to be right here. But what about in the y direction? You can change all the x's to y's. It'll still work. Give that a try, and we'll see how we work it out next time.